Okay, looks like we got most people with us. So before we begin today, just a couple comments about your exam. Overall, looked pretty good. Maybe a little tougher than before. The median was about an 88. As always, if you had trouble with your exam or want to look back at your answers, I recommend scheduling some time, either using my office hours link or emailing me. We can go over your exam individually, or if you're more comfortable meeting with your SI leaders, they can also access that information for you. So go ahead and do that. Feel real free. A couple of you may have seen minor increases in your grades since the exam I went through, and there are a couple alternate answers that I accepted. So check that out, or if you got a notification about that's what happened there. Okay, so for this unit, we're going to begin with our last topic on the renal system before we move into the GI system and the reproductive system. So for today, our topic is acid-base homeostasis and acid-base balance. And here we're kind of combining what we were talking about with the renal system or the urinary system, and drawing way back to when we talked about the respiratory system, because in order to maintain an appropriate pH of blood, we need both. So some of this is going to be recall from a couple months ago, but we'll walk through it. Okay. So we're going to first review pH briefly before we talk about the acid-base disturbances we may see, and then we'll talk about how the respiratory system plays a role here and how the renal system plays a role here. Okay. So brief reminder about pH, right? The pH scale goes from 0 to 14. Low pH is an acid, high pH is a base. The pH of blood is regulated by both the respiratory and the renal systems. And you might already kind of be thinking about the respiratory system, right? We talked about carbon dioxide as essentially being an acid in its function in our body. So you should immediately kind of have an idea about how that might play a role here. But what we want to know here is that small changes in the pH of blood have really large physiological effects, largely due to the effects they have on proteins and the shape of proteins. Proteins, as we know, are really critical to our body, right? We've been talking nonstop about proteins, essentially, right? All our transporters that we talk about, all our pumps embedded in these membranes that allow things to move back and forth, allow chemical reactions to happen in our body, those are all proteins. So if we mess with proteins writ large, we end up with a real big problem. Okay, so the normal range for blood pH is approximately between 7.35 and 7.45. So that's normal. And it's a pretty tight range here. So as we start to deviate from that, we can either have a pH that is more acidic, which we call acidosis. So acidosis is defined as blood pH anywhere below 7.35, because that's on the more acidic range of, that's in the acidic range past normal. Blood is slightly alkaline overall, right? So that's why 7 isn't our normal for blood. And a low pH is the result of too many hydrogen ions, pretty basically. The number of hydrogen ions are kind of how we determine pH. So if blood is too acidic, it means we have too many hydrogen ions, and we're in this low range below 7.35. So we also have the opposite. If blood is too basic, we call it alkalosis. So we can also refer to it as being too alkaline, right? That's a term we use for more basic pH. So that is defined as anything in the higher range, so above 7.45. And this is often going to be the result of too few hydrogen ions. So decreased hydrogen ions lead to alkalosis. Okay. So if we go way farther outside that range, right? We have our 7.35, our 7.45 range we want to be in, lower acidosis, higher alkalosis. If we extend much farther, if we end up with a pH above 8 or a pH below 6.8, this is fatal within seconds, right? So you can be in acidosis or you can be in alkalosis, but if you go too far down that road, you're dead. So this is all coming back to the proteins. As we change the distribution of hydrogen ions or other charged particles that are related to the pH, this alters basically the charges that are surrounding proteins. If you remember way back to ANP1 or even your previous courses, the charges on proteins, the charges in proteins affect how proteins fold. And that means that the charges are really going to change the possible protein shapes. If we're no longer in this strict pH range, we may end up with different folding. So if we have a different shape, that's a problem, because the shape is a lot of what allows the protein to do its job, right? The shape of the protein allows, for example, different substrates to fit into an enzyme, right? If we change the shape of that location where our substrates are binding into an enzyme and they don't fit anymore, then the enzyme can't catalyze that reaction. Or if we change the shape of a membrane protein, maybe it can't bind whatever it was binding and allow it to move through. So it causes big problems. So in general, acidosis, the effects that we see are a depressed central nervous system. So we see neurons not firing enough, not firing as frequently. Alkalosis has the opposite effect. So in alkalosis, we often see a hyperactive central nervous system. And this is obviously before you get to the fatal range. So we have a number of different mechanisms that allow the body to balance out the pH, to stay in that tightly regulated range, right, to do homeostasis. So one of the ways that we can balance out disturbances to the acid-base balance, disturbances to the pH, is using hemoglobin. So hemoglobin acts as a buffer in our body. So hemoglobin, right, can bind or release hydrogen ions, right? So essentially it can soak them up, right? So the equation for this is here. Don't worry about memorizing the equation in particular, but as you can see, right, it can bind a hydrogen ion and become this hemoglobin bound to hydrogen here, right? Or it could go the opposite direction and release that hydrogen ion. Okay. So deoxyhemoglobin has a greater affinity for hydrogen ions. So we can see that kind of here, right? There's no oxygen involved here, right? We released the oxygen over here. So that's how we can tell that, basically. So hemoglobin functioning as a buffer, deoxyhemoglobin is binding on some hydrogen ions, removing them essentially from the plasma. If they're bound into hemoglobin, they're not affecting our proteins. They wouldn't contribute to the pH there. It's really when they're free and we have that charge on them that they're affecting our pH. Okay. We also have bicarbonate ions, and bicarbonate ions are really the main thing we're going to focus on. There are a couple different things other than hemoglobin as well that we'll see referred to as a buffer, but by and large, it's bicarbonate and what we're going to see the body adjusting when we get to renal compensation, so the kidneys and their effect on pH, is the role of bicarbonate. So if you're going to remember one buffer, really remember the bicarbonate. That's the important one. So they act as a chemical sponge using this equation that we actually kind of saw before, right? So a bicarbonate ion plus a hydrogen ion form carbonic acid. And carbonic acid can also dissociate into CO2 and water. And it's going to be important for our understanding of how we're regulating pH and how we're regulating bicarbonate ions to realize that this does go in both directions. All right, so we're going to see in some places carbon dioxide and water come together, form carbonic acid, and then give us our bicarbonate ions and hydrogen ions. And we'll see it the other direction. Okay, but this is why we consider CO2 to be a biological acid, right? Because of this process where we can take CO2 and essentially turn it into hydrogen ions and bicarbonate in the body. Okay, so CO2 is a respiratory acid. We say it's a respiratory acid, basically because the normal role of CO2 is that it's produced by cellular respiration, right? So it's produced by breaking down glucose, and we should be breathing it off during ventilation. Okay, so it's a respiratory acid produced by respiration, should be gotten rid of by ventilation. So that brings us to the calculation of pH. We're not going to actually worry about calculating out the numbers, but what we are going to be interested in is the fact that part of this equation draws on the ratio of bicarbonate ions to CO2. So this is really the part of this we care about, right? So we know we could calculate out pH using this equation called the Henderson-Hasselbalch equation based on our bicarbonate and our CO2. So I'm just going to tell you that to maintain our normal arterial pH, right? So the normal pH in the blood, about 7.4, right? That's in the middle of our normal range. Our ratio here would be 20 to 1, right? So those are the numbers that would give us the normal pH. So we're going to see our two systems basically regulating different parts of this ratio. So our respiratory system, right, is going to be oops, you're on the wrong place. Our respiratory system is going to be regulating the CO2, right? So our lungs should be making sure that we're breathing off appropriate amounts of CO2. And our kidneys are going to be regulating the top half of this ratio. So the kidneys are going to be regulating the bicarbonate. Okay, so anytime we see deviations from this ratio, we're going to register that as a problem, as a deviation from our acid-base balance. Okay, so we refer to this kidney part, by the way, as metabolic regulation. So we'll come back to that when we talk about the direct role of the kidneys, but maybe I'll just type it on while we're here. Okay, so when we're talking about the lungs, we're talking about respiratory regulation. When we're talking about the kidneys, we're going to refer to it as metabolic regulation. Those are the terms when we're referring to these different pieces. Questions so far? Okay. since we have both the respiratory system and the renal system, right, the kidneys, involved in regulating these two pieces of our pH, right, the bicarbonate ions and the carbon dioxide, we're going to be seeing that disturbances to the pH can be caused by either part, basically. So we can have problems with the respiratory system leading to either acidosis or alkalosis, or we could see problems with the kidneys leading to acidosis or alkalosis. And when we have other systems contributing to disturbances in pH, right? Like if you eat something super basic, right? If you were to, I don't know, drink a bunch of baking soda or something, we're going to expect both of these systems to be involved in compensating for any changes to pH. Okay, so we're going to start with the lungs part. We're going to start with the respiratory system, and then we'll talk about the kidneys. Okay. So as we're talking about the respiratory system, if we have a problem with the lungs causing acidosis, we refer to it as respiratory acidosis. And we're going to expect respiratory acidosis to be caused by too much acid, right? That's acidosis. And our acid that we're concerned with here is CO2, right? So CO2 can essentially turn into hydrogen ions, which is our technical chemical definition of pH. But for our purposes, presence of CO2 is a biologic acid, is acidosis. So if you are not breathing out enough CO2, right? If that CO2 is staying in your blood is going to be too acidic. It's going to be too low, below that regulated range, that's 7.35 to 7.45, that would be respiratory acidosis. Or if you have the opposite problem, if you're breathing out too much CO2, right? Say you're hyperventilating, right? You're breathing out lots and lots of CO2. That would be respiratory alkalosis, right? CO2 isn't always bad. We do want some in our blood. So if we don't have enough, that's alkalosis. There's not enough to balance out our normal concentration of bicarbonate ions. Okay. So now we're going to move forward and kind of talk about the mechanisms involved here. So I noticed in the slides from our previous unit, there were some kind of extraneous ones. So if you printed them out earlier, I'm just going to indicate to you that there are a couple we're going to skip through because they're kind of review of things we covered on our last exam. So we're gonna skip this stuff about hormones, which we already covered in our previous unit. We're gonna skip this stuff on MAP because we already kind of covered it in our discussion of ADH and aldosterone. Okay. So we're coming back to our acid-base balance here. So we have our normal pH, 7.35 to 7.45. We now know these terms acidosis and alkalosis refer to a blood pH that is below 7.35 or above 7.45. So when we have deviations, right, as we saw in the previous slides, we have a change in the shape of the protein, which can be referred to as a conformation change. Remember, this word conformation really does just mean shape. Largely affects the excitability of neurons. So acidosis is depressing our central nervous system. Alkalosis is increasing the excitability of our central nervous system. And changes to the pH actually also affect potassium balance. So we're not going to go much into the details on how and why this is, but acidosis actually causes hyperkalemia. So low pH is associated with too much potassium. Alkalosis has the reverse association. So alkalosis to high pH is associated with too little potassium. All these changes do have other effects that we can see in the body. There are actually a lot of poor outcomes of acidosis and alkalosis. So changes to the pH can cause cardiac arrhythmias, so changes to the heart rhythm, that's a problem. Overall causes vasodilation, which has a lot of effects if your blood vessels suddenly start dilating, right, because of pH rather than because of the effects that we want to see in response to hormones or the nervous system. So it's a problem. We want to regulate it. Now, in order to understand what's going on with the pH, it's helpful to know where the hydrogen ions are coming from, because that can kind of help us diagnose when we're meeting with a patient, right, what's going on, what the problem is if we test their blood and we notice acidosis or alkalosis. So one place is just diet, right? So what you are eating and drinking has an effect on your blood pH, and specifically really high protein or high fat diets are going to create a lot of hydrogen ions in the blood. The other way we might see a change in the hydrogen ions, right, is through metabolism. So we have a bunch of biologic acids that we create. So CO2 from normal aerobic cellular respiration, or lactic acid, right? We might see lactic acid from anaerobic respiration from I should say, our fermentation processes, right? If we just do glycolysis, we don't go into the whole aerobic cellular respiration, or also keto acids add into our blood pH. And then we'll also see that the output is important, right? If you have a lot of input, you can adjust that through the output, right? It doesn't have to be a problem that you ate proteins, right? So long as your kidneys and your lungs are able to compensate for it, it's okay. So our kidneys and our lungs are regulating hydrogen ions and CO2. And we'll see that the kidneys are also regulating bicarbonate ions, which act as a buffer on these hydrogen ions. But we would see them directly output excreted in urine. So hydrogen ions are one of the things that we have in urine. And CO2 in the lungs, we're breathing it out. So here's that equation again, just really hammering in that point that carbon dioxide is a biological acid. So if we have CO2, it can combine with water. We have this enzyme carbonic anhydrase that can convert CO2 and water into carbonic acid, and then eventually give us bicarbonate ions, and most importantly here, hydrogen ions. Okay, so we do have a normal concentration of CO2 in our blood. Not all CO2 is bad. So the normal pressure of CO2 in arterial blood is 40. Okay. And that's maintained by the respiratory chemoreceptor reflexes that we discussed in that unit. So we're not going to go back through that now. We'll leave that in the past. But know that there is a normal concentration here. Okay. So our CO2 is coming from metabolism, so from cellular respiration, and it should be output through the respiratory system when you breathe out. If we are not doing these two pieces correctly, right? So if we are not breathing out the CO2 that we're creating, we will see an increase in plasma CO2, right? You're doing respiration, but you're not breathing out. You're going to see respiratory acidosis. So this is a problem with our respiratory system leaving too much carbon dioxide in the blood, which is an acid, so it's acidosis. We could have the reverse problem as well, right? So maybe we see decreased plasma CO2. We're breathing off all our CO2 too much, leading to alkalosis, leading to a pH that's too high. that leads us to metabolic acidosis. So largely, metabolic acidosis is, it did associate it with the kidneys on our previous slide, which is true because we are going to be seeing the kidneys regulating bicarbonate ions, but we should kind of think of it as a catch-all. So anything that's not respiratory, we would kind of wave our hands and refer to it as metabolic. So renal dysfunction is down here, it's on the list. So kidney problems might be a source of acidosis, metabolic acidosis, but we have problems with those other inputs that would be considered metabolic acidosis as well. So if we have a high protein diet or a high fat diet, and that affects our blood pH, that would also be metabolic acidosis. Really heavy exercise, right, leading to a lot of lactic acid buildup, right, might cause acidosis. Lactic acid is an acid. And severe diarrhea would also cause metabolic acidosis. This is kind of the odd man out on this list, because severe diarrhea, the problem isn't actually gaining too many hydrogen ions. The problem with severe diarrhea is this loss of bicarbonate ions. So the loss of bicarbonate ions means we don't have enough buffer to buffer out our hydrogen ions. So those hydrogen ions stay free in the plasma, leading to acidosis. So severe diarrhea, if you are excreting too much bicarbonate in your feces, this is a problem that could cause acidosis as well. So things that could cause metabolic alkalosis, the list is a bit shorter. So anything that's raising our pH because we have too few hydrogen ions or too much bicarbonate, right? So if we ingest something really alkaline, right? Like if we eat a bunch of baking soda is super bitter, so I don't know why you would do that, but you could do it. Consumption of alkaline products would lead to metabolic alkalosis. Renal dysfunction in the opposite direction from our previous renal dysfunction, right? So kidney problems, depending exactly what they are, could cause acidosis or alkalosis. And an interesting one here, right, is excessive vomiting. So this is kind of the converse of our diarrhea. So diarrhea on the previous slide causes acidosis because you end up excreting a bunch of bicarbonate as waste in vomiting, and it's coming out the other end. So we'll see as we move further through this unit that hydrogen ions, we have a lot of them in the stomach. So our stomach is highly acidic, right? We'll talk about gastric acids. So excessive vomiting causes the loss of hydrogen ions from the stomach, which overall causes the loss of hydrogen ions everywhere in the plasma as well, as we try to kind of compensate for that. So those are some of the more common causes we'll see of metabolic acidosis and alkalosis. Okay. So we have ways to defend against changes to pH. So we can buffer out hydrogen ions. We can change our breathing patterns to reverse changes in pH by controlling the amount of CO2, or we can change the function of our kidneys, essentially. We'll see that the kidneys are largely involved in regulating the amount of bicarbonate, although they also regulate the amount of hydrogen ions we excrete in our urine. So they're kind of doing two things here. So we actually do use these three lines of defense almost in order. So buffering of hydrogen ions happens in a pretty short-term time span. It can limit changes in pH, but it can't actually reverse changes unless you add more buffer to the blood. So we're going to naturally have a certain amount of these buffering molecules, largely bicarbonate, but some other things, right, like hemoglobin. We're going to have a certain amount of that circulating in our blood. So as we have problems that either increase the acidity or alkalinity of our blood, those buffers that are present in the blood can soak up those hydrogen ions if necessary, but they can only do that to a certain extent. And it's not like the hydrogen ions disappear totally from your body when they're bound into a buffer. They're still in your body. So we're not actually getting rid of the hydrogen ions completely, so they can't totally reverse changes. In respiratory compensation, we actually can get rid of acids specifically, right? We can get rid of carbon dioxide by breathing it out. So it can reverse changes in pH kind of more permanently, because we're actually fixing the problem as opposed to just kind of slowing down the problem, which is really what's happening with the buffer. Renal compensation likewise can reverse changes in pH. So we consider both respiratory and renal compensation. And those are terms we should know. Right, these are terms, right, that we want to internalize, that we want to remember. Respiratory compensation or renal compensation. Both are considered homeostatic regulatory mechanisms. And in the renal concentration, basically what we're going to see happen is that if we increase hydrogen ions, the kidneys are going to increase the amount of hydrogen ions they secrete into the tubular fluid and therefore excrete in the urine. And they're also going to have us reabsorb and even synthesize more bicarbonate, which kind of brings us back to the buffer, right? So we are actually creating more buffer molecules in the blood, allowing us to limit these pH changes as well. Okay. Reverse can also happen if we decrease our hydrogen ions, right? If we're in alkalosis, we can stop secreting hydrogen ions, which means we keep them in the blood, and we would then also decrease how many bicarbonate ions we are reabsorbing into the blood, meaning that those hydrogen ions in the plasma kind of stay free and unbound. Okay. So buffering is our quick defense. So buffering, we have a couple different buffers. The most important is bicarbonate. So bicarbonate is in the extracellular fluid, so it's like in the plasma itself. So bicarbonate binds with hydrogen ions to form carbonic acid. I also talked about hemoglobin, right? Hemoglobin can also kind of act as a buffer. And then we have some buffers that are in our intracellular fluid, so like in the cells. So some proteins and phosphates can act as buffers inside the cells as well. But most important, really, really most important, is the bicarbonate. Okay. So in respiratory compensation, this is our second line of defense. So it's a little slower than the buffering, because the buffering is just, we have these things circulating or we have these things in our cell. They're kind of immediately soaking this stuff up. That's just a chemical reaction. In respiratory compensation, we actually have to get our body doing stuff. So this takes a couple minutes to have an effect. What we're doing is we're regulating the pH by changing how we're breathing. So we're varying ventilation, either to breathe off more CO2 or to preserve CO2, so breathe off less CO2. So if we increase ventilation, so we speed up our breathing, right? Increase the ventilation, we're breathing out a lot more as we're breathing faster, decreasing CO2, right? Dropping CO2. If we hypoventilate, right? If we decrease ventilation, if we breathe really slowly, this means that CO2 stays in our blood because we're not breathing it off as fast. So increasing CO2. So the overall effects that we will expect to see here, basically, are that we're going to see increasing ventilation, having an increase in our pH, right? So decreased CO2 means we have fewer hydrogen ions, essentially, which means we'd have a higher pH. Decreased ventilation means we'd have more CO2, which means we would have more hydrogen ions, which means we would have a lower pH, which is kind of helpful, right? That an increase in ventilation is an increase in pH. So overall, how this works, we can go through our flow, right? So if we have low plasma pH, which we could refer to as high acidity, acidosis, our chemoreceptors will detect and respond, increase how fast we're breathing, which means we are breathing off a bunch of CO2, which means we don't have as many hydrogen ions because CO2 can essentially be converted into hydrogen ions. So this raises our plasma pH. And as the plasma pH goes up, right, so now we have a higher pH, so we're turning this off by a negative feedback loop. So that is a mechanism of respiratory compensation. For renal compensation, this happens much slower, so this can take hours to days. Now, what we're going to be changing is how many hydrogen ions get excreted, so how much hydrogen is in our urine, and how much bicarbonate ends up in the urine or in the plasma. So we're going to see that the kidneys are able to synthesize new bicarbonate in the renal tubules, which can then end up moving into the plasma and actually then being able to act as a buffer in our blood. Okay. So the effects of increased acidity, so if we're in acidosis, right? So if we're in acidosis, whether it's respiratory or metabolic, when we do renal compensation, what we are going to want to do, right? Acidosis means we have too many hydrogen ions, right? So we might want to pee them out, right? We might want to excrete them. So the way we would do that is we'd start by increasing the secretion of hydrogen ions. Remember, secretion means that we're moving those hydrogen ions into the tubular fluid, out of the plasma. And at the same time, we'd want to reabsorb bicarbonate. So we'd want to move more bicarbonate into the blood so that it's able to soak up hydrogen ions in the plasma. And paired with that, we're going to synthesize new bicarbonate, having essentially the same effect as reabsorption. So this happens, not surprising, in the proximal tubules and in the distal tubules and collecting duct. So normally what's happening is this. In the proximal tubules, we have reabsorption of bicarbonate ions that's coupled to secretion of hydrogen ions. So usually we're kind of trading. We're reabsorbing a bunch of bicarbonate from the tubular fluid, moving it into the plasma. And at the same time, we're taking some hydrogen ions and we're secreting them into the tubular fluid. So one of the ways that we're going to be able to do renal compensation is basically to upregulate or downregulate, right? To increase or decrease that mechanism. So to increase or decrease how much bicarbonate we're reabsorbing, how many hydrogen ions we're secreting. Under normal conditions, the proximal tubule, right? We know it's really kind of specialized for being a bulk reabsorber, right? It reabsorbs lots and lots of stuff. So usually 80 to 90% of the bicarbonate is already being reabsorbed. So there's not that much more we can do in the proximal tubule, right? That only gives us you know, maximum 20% more of the bicarbonate that we could reabsorb here. Hydrogen ions are getting secreted in the proximal tubule. And as we know, sodium is being reabsorbed. We've talked about that as we talked about the kidneys. In the distal tubule, we secrete hydrogen ions just like we do in the proximal tubule. But what we can also do in the distal tubule and collecting duct is to synthesize new bicarbonate ions. And this is happening under normal conditions where we're forming new bicarbonate ions and we're moving them from the cells of the distal tubule and collecting duct into the plasma, so into the blood, where they can then act as a buffer. Hydrogen ions are getting secreted into the tubular fluid at these locations as well, but they're actually kind of buffered out at this point. We don't want our urine to be too acidic either, right? That would be a little painful. So we buffer out hydrogen ions using phosphate ions in urine to maintain urine that is not acidic to the point that it's a problem. Okay. So we're going to take a look at each of these cells. I'm going to try and focus us in on what's new here, basically. Okay. So what we have happening in our proximal tubule epithelial cell, right? So we've filtered a bunch of things through the glomerulus, and the important one we want to focus on to start with is bicarbonate. So we filtered bicarbonate ions that were in the blood, in the plasma, into the tubular fluid. We want to reabsorb those bicarbonate ions, right? We want to keep 80 to 90% of them. That's part of the job of the proximal tubule. So the way we do that is we take those bicarbonate ions and we combine them with hydrogen ions. Don't worry about where those hydrogen ions are coming from yet. All right, so we're going to say we're starting with these filtered bicarbonate ions. We're combining them with hydrogen ions to form our carbonic acid. That's step 2. And then step 3 is we're converting them to water and carbon dioxide. Okay. So now we have a molecule, carbon dioxide, that is nonpolar, that is able to dissolve directly across cellular membranes. So carbon dioxide is then able to travel directly into the cell. So this is essentially how we've gotten bicarbonate into our epithelial cell. We didn't do it directly, right? We didn't have a transporter for bicarbonate ions. We had to have this conversion step where we converted hydrogen ions and bicarbonate ions to CO2. Okay, so now we have CO2 in the epithelial cell. We have more water. And right, this is a kind of repetitive process. So we're now taking this carbon dioxide and converting it back into carbonic acid with some more carbonic anhydrase. And then we convert it back into our hydrogen ions and our bicarbonate ions, right? So we went through a lot of steps just to get these hydrogen ions and bicarbonate into the cell and back into their original forms. We have this kind of transition step with the carbon dioxide to get them in there. Now that we have them in there though, this is where we have the secretion versus the reabsorption happening. So hydrogen ions get secreted back into the tubular fluid, and so they're just kind of looping around, right? So they can re-enter this process here. But our bicarbonate ions are going into the plasma. So here we actually do have transporters that move bicarbonate ions either with chloride ions or sodium ions into the peritubular fluid, from where they can go into the plasma. Okay. This differs a little bit from what's happening in the distal tubule and the collecting duct, and I'm going to try to highlight for you the big difference here. So the big difference is that we consider the distal tubule and collecting duct to be able to make new bicarbonate. So what you'll notice is that we don't have bicarbonate ions here in the tubular fluid, right? None of these molecules that we have in the tubular fluid are bicarbonate ions. Right? We might have some, but they're not involved in this process. So we are making new bicarbonate to move into the paratubular fluid and then into the plasma, right, into the blood. We call it new bicarbonate, but what it is basically is that we are taking CO2 from somewhere, right? It might be from metabolic processes in these cells themselves, or potentially from the tubular fluid. But the important part is we're starting with CO2. We don't start with a bicarbonate ion, right? So we start with CO2. We convert it to carbonic acid using carbonic anhydrase, just like we did in the proximal tubule. Break it up into hydrogen ions and bicarbonate ions. Again, that part is just like the proximal tubule. And then we secrete out hydrogen ions, still the same as the proximal tubule, and we reabsorb our bicarbonate here. So the only real difference in these processes that's kind of important to us is where this CO2 comes from. In the proximal tubule, it's coming from a bicarbonate ion that was in the tubular fluid. In the distal tubule and collecting duct, it actually starts out as carbon dioxide. There was no original bicarbonate ion here. The final thing that the kidney is doing for renal compensation is that it has this molecule called glutamine that it basically can break down to give us a bicarbonate ion. So glutamine doesn't break into a hydrogen ion and a bicarbonate ion like carbon dioxide does, right? It has a different chemical formula. What glutamine does is glutamine breaks into a bicarbonate ion and ammonia, essentially. All right, so we have this process, and then ammonia is going to end up in the tubular fluid. So a component of urine is ammonia. Okay. But here we are essentially freeing a bicarbonate ion, making a bicarbonate ion, and moving it into the plasma. Right, so we're always really moving these bicarbonate ions, whether we're getting them from glutamine, whether we're reabsorbing them from the tubular fluid, whether they started out as CO2. The bicarbonate ions are moving into the plasma, and the hydrogen ions, in whatever form, are being secreted into the tubular fluid, where they are then excreted as urine. Okay. So glutamine really comes into play kind of as a last defense. So this happens during really severe acidosis. So when we're really at the low end of our survivable pH. So we would also consider this a new bicarbonate ion here. Okay, that's time, and that's also basically the basic functions of respiratory and renal compensation. So we'll pick up here on Wednesday and move into the GI system. All right. Take care, everybody. Have a good week. Our first full week in a while.